All right, so yeah, so we're kind of changing gears now. In module 10, we're kind of doing something completely different. And in module 10, all right, welcome those of you who are just joining us. So module 10, we're kind of doing something brand new. And that is we're finding the area under a curve. So just as an example, here's a picture, and it's some curve, and I might want to find, I might want to find the area under the curve between x is equal to 1 and x is equal to 5. So I kind of will shade the area in here a little bit so you get the idea. So the question is, how do you find, assuming we know, we need to know the equation of this function. So assuming I know the equation of this function, how would I find the area under the curve between two x values? And so this is a very difficult question. So that's why, so on one hand, it's intimidating because it's difficult. But on the other hand, it's exciting because, hey, we're going to be able to answer this really hard question. So if we work at it, we're going to be able to answer this really hard question. And so that's really exciting. And the reason why I say it's something completely different is it kind of, at first, well, how do I want to say this? At first, it will have nothing to do with the derivative. I mean, the derivative is what we've been all about in calculus since probably the fourth week of 75A. But now we're no more derivatives. We're not going to talk about that. This problem has nothing to do with derivatives, at least not at the beginning. But it turns out, that's what's amazing about this, is it turns out derivatives are going to get involved eventually. Derivatives are going to be essential to actually solving this problem. And again, that's another thing that's really exciting to me, because I think when I think about derivatives, I think about slopes of tangent lines, right? I hope you think the same thing. When you think about a derivative, you think about the slope of a tangent line. And so to me, I was like, well, this is a line and this is an area. So what the heck could these two things have to do with each other? To me, these two ideas seem completely unrelated. But the amazing thing is they actually are related. And we're going to see that relationship later, but it's going to take a little while to get there. And I guess I should say even more, I should say, it's not really about derivatives. It's about anti-derivatives. Anyway, I'm getting ahead of myself. So, okay, so how do we do this then? Or what are we going to do? So finding the area under the curve is a challenging thing. But here's what we do. Let me bring up GeoGebra here. So maybe what I want to find is, maybe I have this function here. So I have, the function is 100 minus x squared. So there's a graph of it. And maybe I want to find the area under that curve between x is equal to 0 and x is equal to 8. Why? Well, actually, that's a good point. Why would you ever want to find the area under a curve? I mean, for me personally, I would just say, well, because it's an interesting question, and I enjoy answering interesting questions just because I'm curious. But you might wonder, are there practical applications to the area under the curve? And the answer is absolutely. For example, if this curve represents my velocity, like if I'm running a race and I start off, I start off running really fast, but as time goes by, I get more tired and I start to slow down. So this might be the graph of my velocity. And it turns out the area then would be the total distance that I ran. If this is the graph of my velocity, if the y-axis is velocity and the x-axis is time, then the area under the curve represents the total distance that I traveled. So that's a very practical application. And there are other applications as well. So there are definitely finding the area under a curve has lots of uses. Okay, oh, where was I going with that? Okay, yeah, so, okay, but finding the area under a curve, very hard. But so here's what we do instead. What we're gonna do instead is we're gonna cheat a little bit. Instead of finding the area under the curve, we're gonna find the area under some rectangles. Because, and why are we gonna do that? Well, so first of all, the idea is that, well, I guess why, yeah, I said, why are we gonna find the area under the rectangles? Well, in some sense, because it's easy. Whereas the area under the curve, that was hard. So we're gonna try to solve an easier problem instead. And now, of course, if I were you, I'd say, oh, awesome. Can I do that on a final exam, Travis? If you ask me a hard question, can I just answer an easier question instead? Well, no, of course not. But what we're gonna do is, well, why is it okay if we're doing it now? Well, what we're gonna do is we're gonna start by answering the easier question. And then eventually we're gonna see how we can use our answer to the easier question to answer the harder question. And this is really, you know, this is how people solve problems in real life, is they say, okay, I have this really hard problem. I have no idea how to solve it, but I think it's kind of related to this easier problem. And then they try to understand that easier problem really well. And then they try to tie the easier problem to the hard problem. And that, hopefully, if you do it right, will allow you to solve the harder problem. So I want you to keep that in mind. That's what we're doing here, is we're gonna find the area under these rectangles. And so I want you to think to yourself, okay, the area under the rectangles is not really what I want. I mean, I really want the area under the curve, but at least in the short term, this is what I'm gonna have to settle for. Because because at least they're close, right? If you look at the picture, you can see that, well, the area under these four, if I find the area under all four of these rectangles, that's at least kind of close to the area under the curve. You know, if you just look at the picture. So indeed, you can see that, I mean, GeoGebra here is telling us all the answers. So we can kind of cheat. So it turns out, yeah, so just full disclosure here, the actual answer to the area under the curve is about 629.33. GeoGebra is telling us that, but we should pretend that we don't know that, because, you know, in some sense we don't. I mean, we're like, well, GeoGebra, how did you know that? But just for, we can kind of refer to it, but sort of, we really shouldn't know that right now. But what we can do is we can definitely find the area under those four rectangles. And it's not, and let's think about why, let's think about that that's easy. Finding the area, and how would I find the area under these rectangles? And So the way I would find the area under these rectangles is, well, the area of a rectangle is easy. It's just base times height. And so, okay, well, great. The base of this rectangle is 2. And the base of this rectangle is 2. And the base of this rectangle is also 2. So, all right, so that was easy. And then now to find the area of a rectangle, you have to do base times height. And so I need to figure out what the height of this rectangle is. And so how the heck am I going to figure out the height of this rectangle? Well, the key idea is if I look at this rectangle, I can see that the height of the rectangle is, it's where the left edge of the rectangle hits the function. And so did I say left? I said the wrong thing. I meant to say right. So sorry about that. So what am I doing? Let me highlight. I'm focusing on this rectangle right here. And so for this rectangle right here, the height is where the left, I keep saying the wrong word. Sorry. It's where this is the right side. This is the right side. Sorry.
I know what you mean.
Yeah. Okay. Good. Okay. Yeah, sure. But I'm recording this, and so I'm glad you guys are with me. But for people who are watching the recording, I hope you're with me too. Okay. The right side of this rectangle is that x is equal to 2. And so if I plug x equals 2 into the function, then I get 96, I think. Because if you put 2, I'm putting 2 into this function, because the x coordinate, the right hand side, the x coordinate is 2. If you put that into the function, you get 96. Okay, great. So that means we know the area of that first rectangle. The area of that first rectangle is the base is 2 and the height is 96. And so that's going to be 192. And I can do the same thing for the second rectangle. And so I know the base of the second rectangle, but now I need to know the height. And from looking at the picture, you can see that you get the height by putting the number 4 into the function. And so that's going to be, if I put 4 into this function, then I get, don't tell me, 84. And then, so that means that the base of this rectangle is 2, and the height is 84. So this area is 168. Similarly, let's see this, I'm going to put 6 into the function. So this is going to give me 64, and 2 times 64 is 128. And then I put 8, if I put 8 into the function, then I get 36. And 2 times 36 makes 72. And I would bet you a cookie that if you add all these numbers up, 192, why did I write a 6? 192 plus 168 plus 128 plus 72, that had better add up to 560. Because that's what GeoGebra did the computation for us, because it's really smart. But the point is that we didn't need GeoGebra. We could have done this ourselves. And okay, so this is good news and bad news. So the good news is we found the area under the rectangles. That's the good news. The bad news is that that's not really what we wanted, right? What we really wanted was we wanted the area under the curve. And so the area under the curve is not 560. But we're kind of doing the best that we can. We're taking our best shot right now. And at least what we can say is this is an estimate. I mean, we've learned something. This wasn't a complete waste of time, because what we can say is we can say the area under the curve, the actual area under the curve, we know is we now know is bigger than 560. So even if GeoGebra didn't tell us, so pretend we don't know that. Even if GeoGebra didn't tell us what the area under the curve was, we now know that the area under the curve is bigger than 560. And the reason why we know it's bigger is kind of look at the picture. Look at the rectangles and then look at the curve. The rectangles are missing these triangular areas here. So the area under the rectangles is an underestimate because it's missing these little triangular pieces. But this is good information. I mean, it's better than nothing. I mean, when we started the problem, we had no idea what the area under the curve was. But now at least we know it's bigger than 560. So that's cool. All right, so any comments or questions about what I've done so far?
Do we have to use trig to continue?
No, actually, no. Oh yeah, that's a really good question. Yeah, because I assume you're asking that because I called these triangular regions.
Yeah.
Yeah, so it turns, so that's a good observation. But it turns out they're not actually triangles because these are curves. This is curved. Okay. So that's an interesting idea, but I don't think it will work because these are not actually triangles because this is a curve. So unfortunately, I don't think trigonometry is going to work. But I will. So let's see. On one hand, I want to tell you what we are going to do because I don't want to keep you in suspense. But on the other hand, what we are going to do is technically that's coming next week. So I don't want to get too far ahead of where we are. But I can't resist. So here's what we're going to do. Oh no. Well, no, wait. I won't tell you that yet. But I will tell you soon. But let's talk about what this is called. This number 560. Let's give this a name because this number is going to be important for your homework this week. And what this is called is a right Riemann sum. So I'll write that down on the board. This is called a right Riemann sum. And I guess I could, if I wanted to be more specific, I could say using 4 rectangles. Using 4 rectangles. So it is really a mouthful. Apologize for the bad handwriting. So let's decompose. What do these words mean? Okay, so the idea is Riemann, that was the name of a person. So Riemann, that was the name of the German mathematician who came up with this idea. And why do we call it a right? Why do we call it a right Riemann sum? Well, the reason for that was because remember how we determined the heights of the rectangles, and I kept saying the wrong word. The idea was that the height of the rectangle was always determined by the right-hand side of the rectangle. So the height of the first rectangle you got by plugging the right endpoint into the function. And the second rectangle, you took the right endpoint of the second rectangle, plugged it into the function, and that gave you the height. So that's why we call this a right Riemann sum. It's not right as in right or wrong. It's right as in right or left. And then of course using 4 rectangles because we used 4 rectangles. So that's what you're going to be doing this week on your homework. And I'll do some homework problems after I'm done with the general discussion here. But your homework this week is all about doing Riemann sums. And so Riemann sums can be kind of intimidating because there's a lot going on, but I hope that you can become friends with Riemann sums because really they're just rectangles. And I hope rectangles don't scare you. So if you can get a foothold into Riemann sums, then you'll just realize they're just rectangles, and rectangles are easy. So this week's homework has the potential to be very easy if you are able to sort of get that foothold and understand that these Riemann sums are just rectangles. And so that's what a Riemann sum is. So a Riemann sum is just when you draw some rectangles kind of related to your curve, and then you draw some rectangles that approximate the area under the curve, and then you find the area of all the rectangles. That's what a Riemann sum is. So when you hear the word Riemann sum, you should think about this picture. You should think about, okay, it's a bunch of rectangles that are approximating the area under the curve. So now let me see here. Okay, I guess I'm still not going to tell you about next week yet, because I want to say your homework is also going to ask you about left Riemann sums. So let's see here. So the idea is we could do this whole thing again, but we could do this whole thing again, but we could draw our rectangles differently. So for example, what if this time we drew our rectangles so they looked like this? So the first question is, do you think you could find the area of those 4 rectangles? And I guess you don't have to answer out loud. But I hope the answer that you say is, I think I could. I think I could find the area under these 4 rectangles. And I agree. I totally think you could. Because once again, well, we know the base of every rectangle is 2. And then now I have to find the heights of the rectangles. And so what's interesting this time is if you look at this rectangle, this time the height is determined by the left side of the rectangle. So I hope you see that the height of this first rectangle, it's where the left side of the rectangle touches the function. And so this would actually be height 100. Because in this case, the left side of the first rectangle is at 0. And if I put 0 into the function, I get 100. So that means the area of this rectangle is 200. And similarly, I can do the same thing here. I can say, okay, the second rectangle, the height of the second rectangle is where the left-hand side of the second rectangle hits the function. And so in this case, that would be 96. So this rectangle would be 192. And then this one would be, if I plug 4 in there, I get 86. Wait, 84. And so that means this is 168. And then lastly, if I put 6 in, I need to figure out the height of the last rectangle is whatever the y coordinate here is. And the y coordinate here is what you get when you put 6 into the function. And when you put 6 into the function, then you get 64. And so that's 128. And so if you add all these together, 200 plus 192 plus 168 plus 128, that should, GeoGebra tells us, I'm going to trust GeoGebra that that's 688. And this one, this is another Riemann sum. So this is another Riemann sum, because again, when you hear the word Riemann sum, I want you to think rectangles that approximate the area under the curve. So just like we said before, this time the area under the curve, is definitely not 688. Because, and the reason for that is we can see from the picture, the 688 is an overestimate because the rectangles, they slop over. So the rectangles have too much extra. But at least it's close, or it's in the ballpark. That again, it's more information. That at the beginning we had no idea what the area under the curve was, but now we know that it's less than 688. And so this is called, this, like I said, this is a Riemann sum, but this one we're going to call a left Riemann sum. And again, so there's two kinds of Riemann sums. There's left Riemann sums and there's right Riemann sums. And what, you know, so you say, well, wait, what's the difference between a right Riemann sum and a left Riemann sum? Well, it's about how you determine the heights of the rectangles. And so if you use the left-hand side of the rectangle to determine the height, then we call it a left Riemann sum. But if you use the right-hand endpoints to determine the heights of the rectangles, then we call it a right Riemann sum. Oh, and in general, you might say, hey, do we ever mix and match? Do we ever use the left-hand endpoint for the first rectangle and a right-hand endpoint for the second? Nobody, well, we're not going to do that. I guess technically speaking, you could do that, but we're not going to in this class. We're going to keep it simple, and we're going to say, okay, a left Riemann sum means every rectangle, the height is based upon the left side. And for a right Riemann sum, every rectangle, the height of every rectangle is based upon the right-hand side. And okay, and then I did lie a little bit. Besides right Riemann sums and left Riemann sums, there are also midpoint Riemann sums. But I don't want to confuse things right now. There's a video about midpoint Riemann sums, and I'll let you watch that. Because if this all made sense to you, then midpoint Riemann sums are not really a big deal. And a question that often comes up is people might say, well, which is better? Is a left Riemann sum, which is better, a left Riemann sum or a right Riemann sum or a midpoint Riemann sum? Are midpoint Riemann sums better? And the actual answer is no. They're all more or less the same. They all give you estimates. In this case, our left Riemann sum is an overestimate, and our right Riemann sum is an underestimate. But in general, that might not always be true. And they all just are ways of getting different ways of getting estimations. And there's not really, neither of them are any better than the other. So yeah. So when someone asks you, so if someone asks you to find a Riemann sum, you should say, well, what kind? And if they say find a right Riemann sum, then you should do it. But if they say, oh, it doesn't matter, find whichever one you want, then you can find whichever one you want. So, all right. All right. So comments or questions about that? All right. So it's a lot of me talking, but at the end of the day, it's really just rectangles. It's like, hey, and I want to emphasize, pictures are really important here. So sometimes you're going to have problems there where they don't give you a picture. And so I strongly encourage you to draw a picture, because the only way I can do Riemann sums is with a picture. And I think a picture makes it easy. I mean, when I look at a picture, I see, oh yeah, it's just rectangles, and rectangles are easy. Okay. So now, before we do any of the homework problems, let me tell you, spoil the surprise, and tell you where we're going with this. Okay, so where we're going with this is that what you should be saying is, you should be saying, okay, Travis, that was nice. What we discovered thanks to Riemann sums is we discovered that the actual area under the curve is a little bit bigger, that it's bigger than 560, but it's less than 688. Because the left Riemann sum was too big and the right Riemann sum was too small. And so you might say, okay, well, that didn't really, again, if I pretend I don't know the actual answer, you might say, well, that's really not very satisfying, because that's a pretty wide gap there. Telling me that it's between 560 and 688, that's better than nothing. So knowing that is better than we started, but it's really not very good. I mean, that's a pretty big gap there. So here's what we're going to do to close the gap. What we're going to do is we're going to increase the number of rectangles. So, because look at this picture, we got 4 rectangles, and that means there's a lot that we miss when we use these rectangles to estimate the area under the curve. But notice what happens if I jack up the number of rectangles. You can see that, oh wow, now I have a much better approximation. So you can see GeoGebra changed the computations for me. So our GeoGebra did the computations automatically. And so what we can see now is that the gap has narrowed. That now our underestimate is 616, and our overestimate using left-hand rectangles is, if I use 20 rectangles. So if I use 20 right-hand rectangles, GeoGebra is telling me that we get 616. And if I use 20 left-hand rectangles, GeoGebra is telling me the area is 641. So the idea is now I'm getting better estimates. So the moral of this story is Riemann sums give us an estimate for the area under the curve. And the more rectangles you use, the better estimate you get. So the more, so this was Riemann's brilliant idea, is, hey, if I use more rectangles, then I get a better estimate. And so, yeah, how high can this go? 50? So you can see kind of from the picture that if I use 50 rectangles, the area under those rectangles is really close to the area under the curve. And this is where the calculus comes in. And that is, we're going to do eventually next week. Next week, we're going to do the limit. We're going to take the limit as the number of rectangles goes to infinity. Because if more rectangles means better estimate, then infinitely many rectangles should mean perfect estimate. And that was Riemann's big idea. And again, I want to emphasize this might look scary, but again, or yeah, like you might say, how am I going to find the area under all these rectangles? And yeah, you're right. It would be tedious, but it wouldn't be hard because again, these are just rectangles, and finding the areas under rectangles is theoretically easy. So if it's 30 rectangles, well, this is still an easy problem. It's just going to require me to do a lot of tedious computation. Or I could program a computer. A computer could find the area under these rectangles really fast. So anyway, so that's what I want you to think about here, is that the idea is that rectangles are easy. And so theoretically, I can find the area under all 30 of these rectangles if you gave me enough time. And that's going to give me an excellent approximation to the area under the curve. And then I could use 50 rectangles and get an even better approximation. And then I could use 1,000 rectangles and get an even better approximation. And then eventually I could just take the limit. And so, yeah, you can see here, and yeah, you can see that in the numbers over here, that you can see that they're getting closer together. The overestimate and the underestimate are getting closer together the more rectangles we use. And the actual answer is always trapped in between them. So using more and more rectangles, these overestimates and underestimates will hone in on the actual area. Oh man, I love this. This is great. So this is just so cool. Because yeah, because remember where we started. When we started today, we were like, how am I going to find the area under this curve? That's crazy impossible. But now we have a plan. And the plan is just to use these rectangles. So that's what this week is. So yeah, so let's do some homework problems. So that's what this week is all about. This week is all about getting comfortable using rectangles to estimate the area under a curve. And then next week, we'll see how to extend those ideas to find the actual area under the curve. So all right, so yeah, so here's our problem, and it says, okay, it's given us a graph of a function. Create a visualization of a left endpoint approximation for the area under the curve. Okay, so yeah, so your book uses slightly different language here. So sometimes what you might say, left endpoint approximation, what the heck is that? That just means left Riemann sum. So in this section, when you hear the word approximation, it's talking about these Riemann sums. It's talking about rectangles. So yeah, so it's all about rectangles. Okay, so it wants us to create a visualization for the left endpoint approximation. In other words, the left Riemann sum for the area under the curve on the interval from -6 to 3 using 9 rectangles. Okay, so this is once you know what you're doing, these problems are fun and easy because you don't really have to do any work. You just have to create the picture. So the idea is what I want to do is it says it wants the interval to be from -6 to 3. So what I'm going to do is I'm going to drag this little yellow point all the way out to -6. And then I'm going to drag on these homework assignments, you've got a left yellow point and you've got a right yellow point. And I'm going to move the right yellow point to 3. And so what we've got happening now is we've cordoned off the area between x is -6 and x is 3. And then now it's giving me this little slider here that is going to allow me to pick the number of rectangles. And so the problem says to use 9 rectangles. So I want to drag this blue dot up to 9. And so you can see now what it's done is it's made all these little rectangles. It's made all these little dots down here. And now what I want to do is I want to create that left Riemann sum. So I want to make these rectangles kind of approximate the area under the curve. So I take the left-hand point, the left-hand side of my first rectangle, and I drag it up until it touches the curve. And then I now do the same with the left-hand endpoint of the second rectangle. Drag it up until it touches the curve. And I don't think you might worry, oh wait, how do I know I'm hitting the curve exactly? You might say, yeah, Travis, it doesn't look like you got exactly on the curve there. Well, I think that the computer gives you some wiggle room. So when I press enter, the computer is gonna, I think, be generous when it looks up my answer. So all I'm doing is I'm just dragging all of these left-hand endpoints up to where they hit the graph. And now what I've just got here is I now have a visualization for the left-hand Riemann sum that estimates the area under the function between -6 and 3 using 9 rectangles. And that's what you have to do there. So let's see, and let's check to make sure I got it right. I'll click submit, and it said I was right? Yeah, there we go. So those homework problems are kind of fun. You just get to make drag points around and make a pretty picture. So those are really fun. So yeah, any comments or questions about that? So yeah, so give those a try tonight. You might be able to finish that homework really quick. Or if you get stuck, then let me know. Okay, what do they have here? Okay, so I'm kind of running out of time. So if you guys have to bail out, I'm probably just going to keep talking through the break because I'm recording this. So if you have to bail out, I totally, no hard feelings. I understand, and I'll post this video recording up on the YouTube site later. So all right, so what have we got in this problem? So this time I have to make the picture myself, but I don't get the advantage of dragging all the little dots and things. So I have to work a little bit harder this time, but it's still the same idea. So it says, for the following graph, estimate the area under the curve in the interval from 0 to 4 using left endpoint approximation. Okay, again, that means a left Riemann sum. So use left rectangles, and it says to use 2 rectangles. Okay, so how am I going to do this? So all right, so how I'm going to do this is I'm going to say, okay, so it wants the interval from 0 to 4. So I'm going to sort of chop things off here. I only care about what's happening between there and there. And then let's see, it says to use 2 rectangles. So that's another good point. I guess I didn't make a big deal out of this when we were doing the when we were using GeoGebra. But notice that when we use GeoGebra, notice the rectangles all had the same width. That when we did the example, the rectangles all had width 2. And so that's a convention that we always use. When we split the interval up into rectangles, we always split it up so every rectangle has the same base. So when you're making the Riemann sum here, I think, okay, I want to have two rectangles and I want to cover a total distance of from 0 to 4. So it's not too hard then to see that, okay, the cutoff for my rectangles should be at 2. So I should have a rectangle. So I should have one rectangle that goes from 0 to 2 and another rectangle that goes from 2 to 4. And again, the reason for that is because I want to use two, I only want to use two rectangles. So I want to divide this interval up into two equal pieces. Okay, and then it says, so now all I have to do, so I know the base of my first rectangle. The base of my first rectangle is right there. And now I need the height. Well, it says to use the left endpoint. So I take the left-hand side of my rectangle and I go up to where I hit the curve. And then I go straight over. And so that's my first rectangle. And then now maybe I'll change colors for my second rectangle. So for my second rectangle has base from 2 to 4. And so again, since it's a left rectangle, I start at the left-hand side of the second rectangle and I go up until I hit the function. And then I go over, whoa, straight over, sorry, I'm very shaky. And then that is my second rectangle. And now I have to, so now I got the picture and that's good. But now I have to find the areas. So it's like, I need to find the area of this blue rectangle and I need to find the area of this red rectangle. Because that's what the Riemann, so again, because the idea is, I say, when I say Riemann sum, I say you should think of rectangles, you should visualize rectangles, but at the end of the day, the Riemann sum is a number. It's the number that is the area under all the rectangles. So it wants us, so the idea here is basically that, but so yeah, let's forget the fancy language. Just what we could say is we could say the area under those two rectangles is an estimation for the area under the curve. And so now I say, okay, well, can I find the area of those two rectangles? And I think I can. Because let's see, it looks like from looking at the picture, the base is 2 for this red rectangle. For this red rectangle, the base is 2 and the height looks to be about 5. Oops. So I'm going to go ahead and call this one 10. I think the area of that rectangle is 10. And then for the blue rectangle, I see that once again, the base is 2 and the height is 14. Wait, sorry, the height is 7. The base is 2 and the height is 7. And so that makes the area 14. And so if I add those two numbers together, then I get 24. So I think I would say that an estimate for the area under that curve using a left rectangle approximation is about 24. And let's type that in and see what happens. Now my picture's all destroyed. And all right, and that was it. Okay, so let's get my picture back here. So yeah, so there you go. So I hope I made this look not too bad. It's just, can you draw a rectangle and can you find the area under the rectangle? And if I hope you can do, as a calculus student, you ought to be able to do that. You can draw a rectangle and you can find the area under a rectangle. And so if you can do that, then you can do these problems. So all right. So any comments or questions? I'm gonna pause there.